As we look for ways to manage the CO2 from coal, the oil field experience with CO2 takes on new significance. Engineers are using this oil field experience to develop a new strategy for dealing with CO2 from electricity, ethanol, cement plants, and other industrial facilities.
There is a technique called geologic sequestration. Sometimes this is referred to as CCS for carbon capture and storage. Basically, what you need to do in this process is capture CO2 from an industrial source, compress it, put it in a pipeline, transport it to the place that you need to inject it, and then inject it.
And that approach would primarily focus at large emitting sources like power plants, where you could capture millions of tons per year and store those permanently in underground geologic formations.
Most steps of sequestration are well understood from enhanced oil recovery. Others, such as CO2 capture, are still being developed. Right now, it's difficult and expensive to capture CO2 at existing power plants and other industrial facilities.
There are thousands of power plants in the world, and many of them burn coal. In most cases, only about 14% of the exhaust gas is CO2, and the rest is mostly nitrogen with some water and oxygen. It takes a lot of energy to separate that small percentage of CO2 from the rest, and that adds a lot of cost. Engineers and scientists are trying to develop new plants that integrate CO2 separation into the business of generating electricity.
We've taken an approach of trying to find a technology that goes on the back end of the existing plants. That way we can take care of what we got, and then you can always design from there for the newer stuff, and that's how we've tried to approach it.
Although there are significant challenges to capturing CO2 at power plants, oil field operators have nearly 40 years' experience in CO2 transportation and handling.
The pipeline that supplies carbon dioxide has gone under engineering and design, which has safeguarded it for community employee protection and the environmental protection. When we routed the pipeline, it is routed in such a distance from residences and small communities, there wouldn't be any negative impact to the local area. The pipeline has been safeguarded with the appropriate wall thickness, with the proper controls in place with emergency shutdown valves, remote surveillance, pressure surveillance, which would key on any change in operating parameters, which would alert operators at a 24-hour manned facility here at our plant.
Our job is to make sure that we've got all the fail-safes in place, that we limit the amount of CO2 that goes out.
Just as in EOR, CO2 for sequestration is injected at just enough pressure to enter the reservoir, but not enough to damage it.
When carbon dioxide is injected to sequester it, first of all, it's taken up to a pretty high pressure, so it's converted into almost a liquid state, and then it enters the pore spaces in the rock, and it displaces what is there, which in some cases is going to be crude oil, but in most cases is going to be salt water or a brine that's there. It's going to replace that brine and move it away from the injection site. As it's injected, it will rise up against the seal rock, and then it will migrate out away from the injection site.
Geologic storage zones that can hold CO2 permanently are a critical element of geologic sequestration.
To sequester correctly, we need to separate the good from the bad. To identify and separate good sequestration zones from bad sequestration zones. This isn't new science. This isn't new technology. This is basically what oil companies do in their search for hydrocarbons.
It starts with having some storage space for the carbon dioxide to go into. It's going to have pore space. Those pore spaces are going to have to be connected to each other. So when you pump the carbon dioxide in, it can move away from the injection site and out into the storage reservoir. Along with that, you need a seal above the formation that you're going to put the CO2 into, a competent cap rock that is free of fractures and pathways that the CO2 can escape through.
There are 3 types of geologic zones under consideration for CO2 storage: oil and gas reservoirs, saline formations, and unminable coal seams.
Oil reservoirs have proven over millions of years that they can hold buoyant fluids like oil and gas, and so we know that they have competent seals.
There's still more to learn about saline formations and unminable coal seams before we begin to store CO2 in those types of settings. For example, saline formations occur around the world, but their suitability as a container is completely dependent on the local geology. The key there will be finding the right geology that truly has an effective seal.